Hi, welcome to the energy video, and this is where we're going to go more in depth on that mechanical energy aspect that we discussed before. And so, before we move on, let's go ahead and talk about, well, what exactly is the definition of energy? Energy is defined as the ability to do work. So it's the ability of an object to do work, and we'll figure out what work is exactly in the mechanical realm later on. But it has to do with using energy to get accomplish some task. And the SI units for energy are joules. So if we're measuring energy, any energy equation that we have will have the same unit of joules. And I have a picture of a roller coaster right here because a roller coaster is actually a good example of where energy uh, comes into play. There's really only one part of a roller coaster that matters, where we actually have mechanical devices that um, help out, and that's the upward ramp of the roller coaster. And so where I circled, that's the only place that the roller coaster actually does anything to the car. After that, it's all energy and how energy interacts throughout the whole roller coaster. So roller coasters are a good example of energy, and we'll probably pull back some projects or pull back and do some projects over roller coasters as we go along. And I said before in the previous video that mechanical energy is the one that we are going to spend the most time on, or we're actually going to start calculating. So we're going to start off with potential energy, which is the ability of an object to move based on its location. So this has to do with the environment that the object is in. Uh, and the one that we should know the most about is gravitational potential energy. You've probably seen this before in previous classes. I've had students that said, man, I learned this in 6th grade. So this should be somewhat of a review somewhat. And basically, gravitational potential energy is just the ability of gravity to move an object. It is given by the equation of potential energy gravitational equals the mass of the object times the acceleration of gravity, which is 9.81, times the height. Now, energy is a scalar, which means that it doesn't have a direction, which means that my G needs to stay positive. I don't need to include the negative sign, which tells me that G points down. Instead, I need to keep G positive. Now this height, as you'll see in the next statement, says an object's energy has to do with its height relative to a zero location. So wherever we choose our zero height to be is how we measure our potential energy. Um, so it makes the energy relative to the surface, but not its absolute position in space. And so we'll actually see that in my example down here. Let's go ahead and scroll down. And so here I have a ball, and my ball is uh, above a table. Now, if I look at this, then the height of my ball, I would choose that the surface of the table be my zero location because that's the zero height. That's as far as the ball can fall, and so that would be zero. And I will see that my ball is actually using this scale 2.7 or 2.5 centimeters off the table. And then likewise, if I move the ball, but I'm going to keep it the same height as it is, so I'm just going to move it over. And now it's no longer above the table. Instead, it's now above the floor. Its vertical position hasn't changed any, but its height has changed. So if I were to measure this, I would say that it's probably around 4.3 centimeters above the floor now. And then let's say that I pull it over here, and this is the wall, and I hang it out the window. So I'm holding it outside the window right now. I haven't changed its vertical position, but let's say the ground is down here, so I'll make that my 0 point. And we will measure where the ball's at. And now it's at 7.3 centimeters above the ground. So it has to do with how far the object can fall. or where I choose to put my zero height. And if I choose my zero height and I keep it consistent throughout all of my calculations in this unit, your answer will come out correct. So it just depends on where you want to place your zero. I can have a negative potential energy if I choose to have my zero above my ball. But that is okay. Once again, if I keep the same convention throughout the whole problem, it won't affect it having a negative potential energy. Here's a picture of a rock that has some great potential energy. It's just sitting there. It's not really doing a whole lot of things, but it definitely has the potential to fall down the mountain. So let's talk about the other type of potential energy, and that's the elastic potential energy. And this is the ability of an object to move because of a spring or other deformation or reformation. And so here's a couple pictures that I have down here that you can see. I have the spring, and so here I have this relaxed position of the spring, and I can actually compress it, and it's going to push the block forward or in that direction. All right, so whenever I let go of it, it's going to push the ball in that direction. Likewise, if you look here, here is a baseball bat hitting a baseball. You don't actually see this part because it happens so fast whenever you're playing baseball, but your baseball will actually deform and cup around the bat. And then whenever it in that split second after this, it reforms, or the reformation of the baseball actually is what pushes it up in that direction. And I can change that color so that we can see it. So let's go ahead and change the color. So that reformation actually pushes the ball in that direction. So that is where there is a storage of energy in this deformation of the ball. Now its equation is a little bit more complex. We have the potential energy elastic equals 1/2 this item K, which represents the spring constant. And the spring constant tells us how much force is required to compress or stretch the spring for a meter. And then you have x squared, or delta x squared, and that is how far it is compressed. So if I were to look at this situation, my delta x would go from there, from where it starts, which is here, to where it ends, which is actually on this side of the block. So that is my delta x. So here's the relaxed length, here is the compressed length, and then that is the distance compressed. And they already have it marked up there, but my green arrow also shows that this is how far it was compressed. All right, and I'm going to have an example problem where I actually use this equation so that you can see how it has worked. The K, once again, is just a constant that is measured, and it has to do with the object itself. It's not something that you can, that stays the same. All right, the next topic is kinetic energy. Kinetic energy is the amount of energy that's stored in the motion of an object. And we're actually able to store energy in the motion of the object, or in the motion of an object. It's sort of like if I were to have a, let's say I'm playing billiards or pool, and I shoot the cue ball into another ball. Well, I can store energy in that cue ball from the cue, and when it strikes the other ball, it will transfer that energy and give it to that other ball. So I'm storing energy in the motion of the cue ball. And like we said before, there's two types: rotational kinetic energy, which is the amount of energy stored in an object that spins. And we see this in the flywheel in your transmission of your car. And I don't know if anybody knows what that is, but basically it's a big heavy wheel that as your car is going down the road, it spins it. And then whenever you stop, it continues to spin it. And then whenever you take off, that spinning helps your car take off. It gives it an additional torque, and so it stores energy in a flywheel. And then whenever you take off, it helps you, it assists your takeoff. A top, such as one that you play with, a toy top. And then the Earth also has stored energy in rotation, because we rotate around our axis. The next type of energy that we'll actually calculate, or that is translational kinetic energy. Now, rotational kinetic energy has a calculation. but it is in depth. There's not really a set equation for all the different shapes. Instead, you have to look at what shape it is, how it's rotating, and that kind of stuff. So the translational is really what we're going to be worried about. And this is the energy stored when an object is moving in a straight line. Not really in a straight line, but it's just not spinning. It can go like your car down the road has kinetic energy, even though it still turns. So translational just means that it's going down the road. And then its equation is the kinetic energy of an object, and this is translational kinetic energy, equals 1/2 the object's mass times its velocity squared. And once again, I'm going to have an example problem that I work that you will be able to see me use this equation. The units for kinetic energy are joules, so it's not new. Like I said, all of these energies are going to be joules. The velocity here doesn't include a direction, because if you were to put a negative direction in here, a negative squared still gives you a positive. So it's still a scalar quantity. And that is all the information about these three forms of energies that we're going to use calculations on. Make sure you watch the example problem so that you can figure out how to use these equations, and then you'll be able to do it on the practice problems in your book. All right.